Oops. Okay, so our next talk is by Sandra Cerrai. Sandra is a professor of mathematics at University of Maryland. And Sandra, please, the stage is.
Thank you, Oleg. Thank you to the three organizers for inviting me to talk at this conference. It was very nice, and I really enjoyed the whole conference. In this talk, I will present, you see, a series of results that I obtained in several years about the so-called Kramers-Smoluchowski approximation. And I will focus my attention on some more recent results, which are dealing with this sort of approximation in the case the coefficient in front of the friction coefficient is not constant, but depends on the state itself. And the reason why I will focus on this situation is because in this situation, something different happens, something that somehow is a little bit unexpected happens. So you see, the equation that I'm going to consider is this equation here. And as you see, this is a stochastic wave equation. So this is the deterministic part of the equation. And then you have this random perturbation. And the noise that I am considering is of multiplicative type. So I am dealing with a diffusion coefficient that is not constant in front of the noise. And this is the friction term. And as you see, the coefficient is depending on the state. In this equation, we have a parameter mu, which is here in front of the second derivative in time, and which represent a mass, a density mass, a constant density mass. And you see, what I'm interested in is in studying the limiting behavior of the solution of the position of u mu as the size of the mass is going to zero. And this sort of approximation in the literature is known as the Smoluchowski-Kramers approximation, and goes back to the beginning of the 19th century, the 20th century. As you see, this is an equation that is studied in a bounded domain of Rd with a suitable initial condition for the position and the velocity, and with the Dirichlet boundary conditions. You see, just to give an idea what sort of condition I will assume on this, on the various terms that are in this equation, you see, what we assume is that for the coefficient that is in front of the derivative in time, we assume that this is a strictly positive and bounded coefficient. And of course, this is a fundamental assumption. We need also some smoothness, say class C1, but what is really important is that this is a strictly positive and bounded. The condition on the nonlinearity F in the case of non-constant gamma, what I will assume is that this nonlinearity is Lipschitz continuous and satisfies suitable growth conditions. And in terms of the noisy perturbation that is here, what we assume is that the noise is a cylindrical Wiener process that is white in time and colored in space. And the reproducing kernel of this noise will be denoted by HQ, and is just the Q of the space of square integrable functions. And the coefficient sigma is a mapping that goes from square integrable function into the space of Hilbert-Schmidt operators defined on the reproducing kernel with values in the space of square integrable function. And this operator is bounded and Lipschitz continuous. I would like to make you notice that you see here this noisy perturbation is smooth in the sense that sigma maps L2 in the space of Hilbert-Schmidt operator, but what I would like to stress is that here we only require that this is a Hilbert-Schmidt with values in the space of square integrable function, and we do not require higher regularity here. And I will come back to this if I will have time at the end. Here in this talk, I am assuming that the nonlinearity F is Lipschitz, But for some of the previous results where we are dealing with a constant friction term, in fact, one can consider a more sophisticated situation, and so one can consider more realistic cases in which this f is not Lipschitz continuous, but for example, is a polynomial of odd degree with a leading coefficient that is strictly negative. So we can consider this class of situation. But in the case gamma is not constant, somehow we have to restrict to this condition on f. As I was saying, this is a long-term project, and in the case of constant friction, what we proved together with Mark Friedling was that the position u mu converges as mu goes to 0 as in the small mass limit, u mu converges to the solution of the corresponding parabolic problem. So somehow you see that in the case of a constant friction gamma, you have a perturbative result. If you think of your equation, in your equation you had mu times the second derivative in time. When mu goes to 0, you can think that you cancel that term and you have the convergence to the corresponding parabolic problem. And what we prove is that you have convergence in probability in the space of continuous paths on a bounded interval. This is important, on a bounded interval with values in the space of square integrable functions. Later on, we could improve this result to the case, you see, instead of proving a convergence in probability, one can in fact prove a convergence in LP sense. And this was done by, you see, working in a more accurate way with you see the transition semigroup that associated to the linear deterministic problem. This is, of course, a semigroup that depends on mu, but working more in a more accurate way with this semigroup, one could prove that, in fact, one has this sort of convergence. And one could have also some, you see, estimate on the rate of convergence in this particular case. While in the previous work with Mark Friedling, the result was proved by using tightness, and then you see the classical approach by using the Scorupol theorem and so on. In this case, we could prove some bound, okay? And these very same arguments that were used in the previous case when we were considering scalar equation can be adapted when you replace a scalar equation with a system of equations. And so you see, if you replace your gamma with a matrix whose eigenvalues have all a strictly positive real part, you really see that the same arguments can be used and nothing different happens. Okay, so going from scalar equation to systems somehow is not a problem. And we will see that in the case of non-constant gamma, this is not the same thing, the same story. So going from scalar to system is changing things in a drastic way. Okay, so what happens when you have a slightly different situation, when you don't have a constant friction term? So for example, with Mickey Saliens, we consider the case in which you replace your friction with a magnetic field. So instead of having friction, you have this rotation, and so you do not have anymore the condition that I mentioned before. You don't have anymore a matrix which has eigenvalues with strictly positive real part, and so this means that the situation changes drastically. So if you replace a times the derivative with M vector product with, and M here is constant, okay? I'm not considering M that is changing, that is depending on the state. But if you take M constant, and so a constant magnetic field, then you consider this a sort of term, the situation is completely different. And what is possible to prove is that you don't have anymore the convergence to the corresponding equation, first order in time, where you just neglect the second order derivative and you take mu equals 0. So this limit does not exist. Nonetheless, you see what we did was to regularize the problem and to add a small friction, and in the double limit we could prove the convergence, in this case not to a parabolic stochastic PDE but to some hyperbolic stochastic PDE, but still we could prove a limit, but only after regularization of the system. Why this approximation is, one of the possible reasons why this approximation is important is because this approximation is stable with respect to other important features of the two systems. So you see, when the mass is negligible, you can replace the second order system with a first order system with all the advantages that this may have. Dealing with a first order system is, in most of the cases, much simpler. And so this is a very good thing. But somehow this approximation is stable even if you replace, for example, a bounded time interval with an infinite time interval. And so what was important for us is to compare the long time behavior of the two systems and to compare these two and to see how this approximation was compatible in the long time setting. And what we proved was both, what we consider was both the comparison of, you see, we work both with stationary solutions of the second order equation, and what we proved is that if we consider a suitable Wasserstein distance with respect to a suitable metric that you put in the space of a square integrable function, we could prove that these stationary states are convergent to the unique invariant measure of the parabolic system. And in this argument, of course, we needed to have uniqueness for the limiting system. And under this condition, we could prove the convergence of stationary states. And then the second thing that we did was to consider, you see, to study the Smoluchowski-Kramers approximation, so the small mass limit together with the small noise limit. And we saw how, you see, this double limit behaves well. And what we proved is that, we concentrate our analysis to the problem of the exit of solution from a functional domain. And what we could prove is that, in fact, the quasi-potential that describes the exit of the position in the second order equation converges to the quasi-potential that describes the exit times of the parabolic equation. And so we saw that there was a consistency in the small mass limit when we consider the small noise limit as well. So this is a very good approximation when it comes to the long time behavior of the two systems. And this was a work that was done in collaboration with Nathan Glatols and with Nicky Salins. So now let's see what happens in the case of a non-constant friction. And here I put also constraints, but I will talk later about equation with constraints. So here I will only talk about non-constant friction. So in many relevant situations, you cannot think that the friction is constant, so you may you want to assume that this friction is depending on the state. And so what you have here is not gamma constant, but gamma is a non-negative function. And together with Guangyu Shi, what we have studied was the convergence, the limiting behavior still of the position in the second order equation when mu goes to 0. And what we saw is that we don't have a convergence to the parabolic equation. It would not be a parabolic equation. In fact, it would be a quasi-linear stochastic equation. But So we don't get the equation where you just cancel mu, you take mu equals 0, and so you have the limit. But in this limiting process, there is the creation of an extra term, which comes from the interaction between the friction, the non-constant friction gamma, and the presence of the noise. So because of the interaction of these two terms, there is a noise-induced drift. And this is what I will talk about today, and I will show you how you get this extra term. So we start from the second order equation for a fixed mu. For this equation, as far as we know, there was no well-posedness theory because of the presence of this non-constant gamma. And so we had to study this equation for fixed mu. And the idea, and I mean, the natural idea is to think of this term here, which we have, this term here, and to replace this product, which can be a nasty term, to replace this product just with the time derivative of a new variable, which is a g of u mu, and g, of course, is defined in this way. The advantage of this is because, you see, as I was saying, you replace this product with this single term, and this g, because of the very nice condition that we assume on gamma, is a very nice function, and so this transformation is the best transformation you can imagine. And as you can imagine, if you don't have this nice condition on gamma, you see things are getting more complicated. And so we rewrite the system in new variables. So we introduce this new variable eta, which is defined as the velocity plus g of u divided by mu. Here there is no problem because mu is constant, but you will see that when we want to get some a priori bounds, then things can get tricky there. And so we replace the system with this nice equation. And for those of you who know me, I mean, you know that I like this equation. This is an abstract evolution equation, an abstract stochastic evolution equation, and this is a very nice thing, where of course you have this new coefficient sigma gamma and a mu, sigma mu, sorry, and a mu, and a mu now is not anymore a linear operator, but is a linear operator, which in fact we will see has some very nice properties. Okay, so because of this, as I was saying, is that you can replace this system with this abstract evolution equation, and here of course z is equal u, and then is a v plus g of u divided by mu. Okay, this is the change of value. So we study this equation, and by studying this equation, what we prove is that for every initial condition in H1, this is the regularity that I need H1 times L2 for position and velocity. What we have is that there exists a unique adaptive process that solves my equation. And this existence result is done by using the theory of nonlinear M-quasi-dissipative operator. So you first approximate regularize your problem, and then you prove uniqueness. Okay, so now that we have a well-posed equation for every fixed mu, our point is to study the limiting behavior of u mu as mu goes to 0. And what we want is to study this limit, to prove that this limit exists, and then the second part is to identify this limit as the solution of a suitable quasi-linear parabolic equation where there is this extra drift that is appearing. The way we do this is by, you see, using proving tightness, and then you see using the Scarlett theorem and taking the limit in the equation. So the key point here is proving a priori bounds. And if you have looked at the equation till now, you see that there is some tricky dependence on this parameter mu, which is everywhere appearing as 1 over mu. And so the problem here is to be able to have some nice a priori bounds. And this was the next step, proving these a priori bounds for the position and for the velocity in the suitable topologies that somehow are needed in our analysis. So if we start from the energy estimates, we get this first estimate, and this first estimate somehow is not surprising. This is something, and this involves the sup norm of the position in the L2 norm and the integral estimate of the position in the H1 norm. So for this one, it's something that it's reasonable and is good. But then we go to the next bound, because of course this bound is not enough for what we want to do. We want to have something more. And then if we consider a uniform norm, if we want to have a norm for the H1 norm of the position and for the L2 norm of the velocity, plus this extra term, this integral estimate for the L2 norm of the velocity, you see that this term appears. And the presence of this term is due to the fact of the presence of the noise and the presence of the Laplacian. If you want to get this type of estimates in finite dimension, you don't have this problem. In finite dimension, this term here is a good term. You have a CT, you don't have a CT over mu. But in infinite dimension, you have this term, and this term, of course, is something that you don't like. You don't like because you see, there are already some good things in this bound. Look at this part here. You see, this is a mu and this is a square. So from this bound, what we get is that this at least is bounded. But this is not enough because I would like here to have a square. Okay, I would like to have something like this, which is what you get in finite dimension. Unfortunately, we cannot get that in infinite dimension, but we can improve the previous bound, and what we get is something like this. Okay, so here, instead of having mu as before, we have a square root of mu. Okay, so we can improve a little bit this bound. But this improvement is crucial for what we want, because this improvement allows us to prove that this part here, which with the previous estimate was just bounded, now this term here is in fact going to zero as mu goes to zero. And this is really what will be fundamental for our analysis. Okay. Once we have the a priori bounds, I can state the final result, and then in the last 10 minutes, I think I will discuss about some further developments of this result and some words about the way you get this result. So what we have is that if you fix an arbitrary delta positive, an arbitrary p less than infinity, you have the convergence of u mu, the position of u mu to this u with respect to these topologies. Okay, so you have uniform in time, but with values in h minus delta for every delta positive, and LP in time with values in the space H. So you have convergence in probability, and the limiting object is the solution of this equation here. And what is this equation? This equation is a quasi-linear parabolic equation. You see, you have this coefficient in front of the Laplacian, okay? Then, of course, you have f divided by gamma. Then you have in the noise sigma divided by gamma, and this would be what you expect. But then you have this extra term here, which is appearing, and as you see, this is coming from the interaction of the noise. This is the part that comes from the noise, and the fact that gamma is not constant. Okay, so because of the fact that gamma is not constant, and because of the fact that you have a noise, you have the creation of this extra term. Because of the assumption that we have made on our, I mean, at the beginning, I didn't stress too much this, but you see, this is a perfectly well-defined extra term, because I was assuming that sigma of u was taking values in the space of Hilbert-Schmidt operators defined on the reproducing kernel, and this is the basis of the reproducing kernel. So what you get is that this function here is in fact a function L1 of D, okay, and but it has a very nice dependence on u. So this is an equation that we will see can be treated nicely, and there is some theory available for the analysis of this equation. Not completely, and I will tell you why, but there is a nice analysis for this equation. Okay, so this is the limiting equation. So let me first say a few words about the result. Why this? I mean, what is in this result? So let's consider the case when sigma is constant. If you go back to the case when sigma is constant, okay, and you look at this term, so what you realize is that this noise-induced term coincides with the Stratonovich-Twitter correction. And so what you can think is that, you see, you can restate your result by saying that in the small mass limit, you have the convergence of the quasi-linear parabolic equation, where you don't have an extra term, an extra drift created, because you can interpret, you can change, you can go from the Ito integral to the Stratonovich integral, okay? So the limit is a quasi-linear equation with a Stratonovich integral. But what is important here is to notice is that when sigma is not constant, this is never the Stratonovich-Twitter correction, okay? So in the general case, you have a non-constant diffusion coefficient in front of the noise. What you have is that you don't get the Stratonovich equation, the quasi-linear parabolic equation with Stratonovich correction. You get something different, okay? Okay, so this is what I wanted to say. And let me say a few words about the proof, I mean, how you get this. So instead of working with u mu, as we did in the case of a constant friction, we worked with this new variable. And this is the natural variable to study this problem, simply because you see this term gamma u dtu is just dt g of u, okay? So you realize that this is the natural variable that you want to use. And so with this change of variable, we consider rho mu, and we have studied the tightness of this family of probabilities, the distribution of rho mu. And what we could prove is that for every initial datum in the space H1, this family of probabilities is tight in this space. And this space is given by the intersection of this space and this space. The reason why I wrote this, and I would like to make you notice this, is that in fact we were not able to prove tightness in the more natural space that would be L infinity 0t with values in H. This was not possible, and this is why the limit, in the small mass limit that we get this with respect to these different topologies. So we couldn't prove tightness here. We couldn't prove tightness here, but we only could prove tightness in these two spaces. And the proof here, of course, follows from the previous a priori bounds, and then from some characterization of, you see, LP function with values in the Banach spaces. But this is all somehow classic, okay? So once we have the tightness for these families, we want to see what is the equation that they satisfy. And so what we realize is that this rho mu satisfy this equation here. And you see why I was so much, you see, worried about this term here. I was so much worried about this term here because this is the term.
Sorry, there is maybe some problem. Your screen is frozen. We don't see.
Let's see if I redo this, because usually when I do this. What is happening? One moment. Yeah.
Yeah, now it's much better. Okay.
Okay, so what we get is that this rho mu satisfies this equation. And as you see here, there is this extra term, which is the extra term that I wanted to kill. Okay, and this is why I was so much worried about that. And because I wanted, this is why I wanted to get those bounds before. Okay, so I wanted to kill this term. And what we get is that this rho satisfies this equation. And then, of course, due to tightness and everything, what one can prove is that one has a convergence in distribution of rho mu to the solution of this problem here. Okay. And the problem and the fact is that in fact the previous equation that I wrote has a pathwise uniqueness, and so in fact the convergence, instead of being in distribution, is a convergence in probability, and we get the result. And then you see we got the limit for rho, and now we go back to U with the inverse transformation. We define U as a G minus 1 of rho, and this is again a nice object because G is a nice transformation. And so what we get is that U mu converges in probability to U in this space as mu goes to 0. And then you see we want to identify what is U. And we identify U by using a generalized Ito formula, you see, first introduced by Perdue, and then in the same, you see, this Ito formula has been generalized recently by the Bischoff, Manova, and Vauvel when they have studied quasi-linear stochastic parabolic equations. And then, I mean, we needed to do a slight modification to adapt to our situation. But at the end, by using the Ito formula, what you discover is that U satisfies, the limiting object satisfies this equation. And this is exactly the equation that I wrote before. Okay, so the whole point is that you don't want to get the limit for U. You want to get the limit for G of U. For G of mu, you have a perturbative result, and then you go back to the equation satisfied by U, and you get this extra term. Some words about some further developments, and then probably we'll discuss this also with Nicholas later. But you see, the first important question is what happens when you don't have this nice condition on gamma. So what you have when gamma, for example, is not bounded. If gamma is not bounded, then this means that you cannot use the theory of a non-degenerate quasi-linear parabolic equation. You need to have something different. You need to consider the degenerate quasi-linear parabolic equation. There is a theory, but one should see how this fits in our problem. And then what happens when gamma is not strictly positive? And of course, this is opening a huge box of problems, and you see. So, but I think this could be interesting to study. And then what happens when you don't have a single equation, but you have a system? And here the analysis is very different. Why? Because you have your term gamma u dt of u, and you cannot write anymore this as a dg of u mu. Okay, you cannot do anymore this transformation when you have a system. And if you cannot do this transformation, even at the level of the a priori bounds, you are lost, and you need, you need different arguments. And then even the well-posedness of the equation requires very different arguments and more sophisticated techniques. So you see, the case of system is not just a trivial generalization, but I think this would be interesting because you see, in this type of situation is relevant to know what happens with systems. And the last remark that I wanted to say is that, you see, another situation that is of interest is when instead of having a non-constant friction, so assume that you have a constant friction, but you have your equation that is confined to live on some manifold. So for example, you can think that your solution is confined to live on a unitary ball in L2. And still what we expect compared to what happens in the final dimension is that you have the creation of an extra drift. So you don't have the convergence to an equation, a parabolic equation with constraints, but you will have the convergence of a parabolic equation with constraints and with an extra drift. So this is what I expect, but of course this has to be studied. Okay. I think this was all what I wanted to say, and so I say thank you.
Okay, thank you very much, Sandra, for a very nice talk. And now we will pass to the discussion, and then we will have questions to both you and Nicolas. So the discussion will be by Nicolas Tapia, who is my colleague here at Weierstrass Institute in Berlin, and also he's affiliated with Technical University Berlin. So please, Nicolas, you can start.
Okay. Thanks, Oleg. And first of all, I would like to thank Sandra again for her nice talk and nice discussions as well while preparing these slides. Yeah, so I should also say that I'm really more a friend of the field than working directly on it. So perhaps the audience will forgive me if my questions are too naive, but okay, I'll try my best. So to begin with, I would like to take it as a step back and kind of review this historical context of this Smoluchowski-Kramers approximation. And what they considered initially is a bunch of particles, say n particles. So this is a multidimensional system of ODEs that move in a random force field, which is of this form, and they are subject to friction, which is this term with the gamma here. So the Newton's equation for that kind of motion looks like this, and they were interested in taking the small mass limit, which means taking mu to 0. And why is this interesting is because if we're working at the elementary particle level, this is essentially what you're looking at, and if you are able to show that this complicated equation is well approximated in some sense by a simpler equation, then you're in a much better position to try to understand what's actually happening. Yeah, so the usual technique here is to rewrite this as a system of first order ODEs and try to see what happens as mu goes to 0. And the classical result is that under suitable assumptions, the solution to the x mu, so the x mu solution here, which is sometimes called a physical Brownian motion, converges to actual almost a mathematical Brownian motion, at least in the case where f is 0 and sigma is constant. So if you have a physical Brownian motion, so a particle moving in some potential, and you look at various particles with very small mass, what you see essentially is just plain old Brownian motion, maybe with some coefficient. And if I understood correctly, what Sandra is interested about is sort of an infinite dimensional version of this kind of motion. And so I put the equation here on the right to see more or less the comparison between the two. And you will see that they look morally the same. So there's a second time derivative here, while there's a Laplacian that doesn't appear on the left. And there's a noise term here that's white in time. And we have some suitable initial conditions. And so again, the problem is try to study what happens when mu goes to 0 in some topology. So as Jonathan pointed out in the previous talk, as contrary to the left, on the right, there are multiple topologies where this convergence could happen. In the left, there's essentially not that many. Yeah. So it's kind of more canonical what you can say, but on the right, it's really more difficult. And some of the results that Sandra presented are summarized here. So for example, in the case that the friction coefficient here, which is denoted by gamma, is constant, is a positive constant, then as mu converges to 0, the solution of this wave equation here actually converges to the solution of parabolic equation with some forcing. So in this sense, nothing strange is happening, and one gets what one would expect in the limits. And this is, of course, very nice because, again, as in the case of a finite dimensional system, when working with particles with very small mass, one can just replace this complicated second order equation by just a parabolic equation, which is easier to understand. And the nice thing is that one can also do similar kind of results under suitable conditions when the friction coefficient is not constant, and this is the main results, one of the main results that Sandra presented. And what happens in this case, so as soon as the friction coefficient is not constant anymore, one gets this complicated quasi-linear parabolic PD. So it's not as easy as the previous case anymore, and one gets this kind of correction terms. And again, as discussed, the main tools for the proof of these kind of results is, first of all, a generalized Ito formula, which was developed by these authors and others, and the solution theory for the equation with positive mass. And one thing to note is that as soon as the diffusion coefficient here, so the term multiplying the noise is a constant, this actually kind of falls back to what one would expect. So we get, again, a quasi-linear PDE, but in the Stratonovich form. But this looks closer to the what the limit should be. But as soon as sigma ceases to be constant, then this correction term appears here. So now I would like to ask a few questions which popped up while we were discussing. And so the first one is, I guess, to have this generalized Ito formula in order to arrive at this result, the regularity of the noise, I mean, the fact that it's colored in space, it's quite important. So how far do you expect, or are you actually able to push this kind of assumption?
You see, of course, you see, what we did was heavily based on the results, the fundamental results of these authors that you mentioned, the Bischoff, Manova, Vauvel, Zhang, when they studied this class of quasi-linear stochastic parabolic equations. And you see, if you go to their papers, you see that in order to study the well-posedness of these systems, of these equations, you see, they have to assume a quite strong condition on the regularity of the noise, and in particular, when dealing with the existence of solutions, they were assuming some condition on sigma that were stronger than the condition that we assume in our paper. So as I said, now you have this condition that sigma maps L2 in the space of Smith operator from the reproducing kernel with values in L2. Okay, in their case, it's more than that, is with values in some Hilbert space. And this is because of the work that they do with the existence. In our case, somehow, we don't care about the existence in the sense that we have this family of solutions, U mu, and or rho mu in this case, I mean, and what we do is to prove that this rho mu converges to some object. So we have the object, and then we have to identify the object. And in the identification of the limiting object, what we are more interested in is the uniqueness of solutions for this quasi-linear parabolic equation. And when you go to uniqueness, somehow you see that the condition that you need is the condition that we assumed in, in our paper. So you see, if you want, compared to the existing literature, this is a small improvement in the sense that you get existence for this class of equation with less regularity of the noise, because you see, we get the object as a limit of this. In our analysis, we have considered sigma with those conditions, and you see, this was the natural condition for us to give a sense to this noise-induced term. We didn't really work very much on trying to understand if we can have, you see, less stringent condition on the noise. And I think this would be a very interesting direction of analysis, also because you see this method would, because usually you do the small mass limit because you are interested in you see, you are coming from a more complicated system and you want to go to a more simple system. But you could also look at this approximation as a way to understand a limiting complicated object in terms of this approximation. So this could be a nice direction, but yeah.
Yeah, so thanks. Yeah.
In the sense that I don't know what we can get with a less strong condition for the moment.
Okay, right. So maybe let me continue in the same direction of kind of weakening the regularity of the noise. And so when I think about you know, systems of ODEs or SPDs, I'm immediately led to think about rough path, which is what I actually work on. And when I saw your talk, I was reminded of this paper. I also, when looking at the Smoluchowski grammar business, and so this kind of modification, or let's say Ito correction that we see in your result, it actually also appears in the finite dimensional system when you put it under the lens of the rough path theory. So there's this paper by Peter, Paul, and Terry Lyons that says that when one looks at the solution of this system as a rough path, then one can actually get a stronger statement, that what I showed in my first slide. So one can go actually to a better topology, I mean, to a stronger topology, right? So and this actually, this convergence also comes with explicit rates, and so perhaps one can try to do the same as for your case, right? So, and what I wanted to say here is that, of course, when one tries to lift this this kind of regularity conditions on the noise, one falls immediately into the realm of singular SPDs, and all the classical tools really immediately break down. And even for simpler equations like this, Ito type formulas, which were apparently very important for your kind of results, are hard to get. So yeah. I know of a work by Lorenzo, and there's also this paper by Gradinaru, Nordin, and Tyndall. There's also Lanconelli, and I know that Carlo has also worked on this from the point of view of regularity structures. And so for this type of equations, one can actually get, even in the white noise case, one can actually get an Ito formula. But yeah, I really don't know if this is possible for more complicated equations. But it seems to be a nice question, maybe for the audience, or for you, if you know if somebody's working on this.
No, I don't know about this, but here in the audience there are experts that could probably jump in the discussion. But as I was saying, I think that you see, if you look at this from the point of view of, because you see, in our analysis, the regularity of the noise was not an issue. Our, you see, consideration was somehow to other aspects. But if you look at this from that point of view, then you see, as I was saying, for example, taking this limit can probably say something about limiting objects that are not nice. But of course, this requires some new tools, because the etotype formula that we used is somehow, you see, a good one.
Right.
A nice formula that applies in a nice situation. But yeah.
And so actually, how stable are your results under, how continuous are your results, if you want, as mu goes to 0? So, I mean, how strong is the convergence that you can get to say something about the limits?
In this case, you see, I don't know, in the sense that, again, the limit is obtained by using tightness. You have tightness, and then you have scalar code, and then you have a weak limit. You identify the weak limit as a unique object, and then you have convergence in probabilities. This is the scheme. As I was saying at the beginning, you see, and in this case, this is the only thing I can say. There is nothing more that I can say. In the case of gamma constant, then this means that the linear deterministic part of your equation that involves the Laplacian minus gamma, the first derivative. So that you have somehow a linear problem that depends on mu, and one can have a very delicate analysis of the behavior of the solution of the deterministic linear problem depending on mu. And then in that setting, one can have, one can quantify this convergence. And so in that case, really, you can get bounds depending on mu, because you don't use tightness and convergence. You really take the difference of the two solutions and you see what happens in that case. And there you have nice bounds, yes. And then you can also take the nonlinear situation if you have, of course, nice nonlinearities. I'm not claiming that you can do this with complicated nonlinearities, but with nice nonlinearities you can do that, and so you have an estimate. But somehow in this general situation, and I know that there is currently some work in the finite dimensional case by people like Charles-Edouard Breyer and some of his collaborators, where they are interested in studying, you see, this type of problems. But for the moment, they are considering the finite dimensional situation. So,
okay. Thank you. So I'm done.
Okay, well, thank you very much for a very interesting discussion. So are there any questions or comments from the members of the audience about this story, about Ito's formula? Maybe somebody wants to comment. Okay, so while people are thinking, so let me ask a very vague question to Sandra. It's also very vague. So I'm a little bit puzzled here. So here, the noise is your friend or your enemy? So somehow without noise, things are converging as well?
No, here the noise is my enemy.
Okay, and is it possible to construct an
and as you said, the noise is absolutely my enemy, and especially when it comes to proving a priori bounds. The fact, you see, is the presence of the noise and the fact that I have to take care of the Laplacian. And when I want to do my a priori bounds, I have the emergence of this term, which goes as 1 over mu, and this term is bad. And this is why I cannot get the same a priori bound that you would get in finite dimension. In finite dimension, you get better estimates, which are somehow the estimates that you would expect. You would expect that mu times the square of the velocity is bounded. This is somehow the natural, you see, behavior that you would expect. But in the case, in infinite dimension, you don't get that. And the noise is your enemy. Yes.
I was just thinking of maybe like not in this specific stuff, but in this whole theory, whether one can cook up an example such that without noise, things do not converge, and with noise, one thing converges to another. For example, because your parabolic PD is ill-posed without noise, but then, well-posed with noise, or something in this.
I never thought, but for example, look at the limiting equation that you get, the creation of this extra drift, it comes because you have a noise. If you don't have a noise, then you don't see any of that. So in the small mass limit, if you don't have noise, you don't have any, I mean, it doesn't really make a big difference if you have gamma that is constant or gamma that is not constant. The difficulty for gamma constant or gamma non-constant is in the analysis of the second order equation itself, in the well-posedness of that equation, but you can handle if you have, yeah, especially in the scalar case, it's not, you can do that, yeah.
Okay, thanks for your explanations. Are there any other questions from people in the audience?
Maybe.
Oh, Carlo.
If I want just a small remark, so it was mentioned in the last, hello. So it was mentioned in the last slides that you were looking for methods that they do not use the unexplicit, so that they can work also with systems of equation and not, usually usually a Roth path point of view should be more stable from this point of view. So from this, for example, there are several works on Roth PD where it is possible to give a meaning of a system of equation, and so you don't need to, and there is also an intrinsic gradient, and you don't need to express this as the gradient of a function.
Okay, so what
something like you don't, but so that could be a potential, so a Roth reinterpretation of the system, but of course there is the complexity of being infinite dimensional and so on. So, but that might be so something that can be interesting for a system. That might.
Okay, so what you're saying is that somehow you can handle these systems and you find a way to.
No, I'm saying that this Roth point of view, it might be nice to look at the system directly as it is, so without rephrasing it in the term of this additional function. And so this you have this dt of times, you rewrite it as a dt of bigger function. It might be, but at the same time, it's harder to get this system from a Roth point of view. So it might be better because you solve, but it's very hard because you have infinite dimension and you have the wave operation, and it might be, but okay, it is something that you need to think, but.
Yeah, in fact, there is a paper by, I think, Martin Heirer and Hendrik Weber, where they study, you see, Burger's type equation, but for systems.
Yeah, exactly. That's exactly the.
Yeah, so you were thinking of that. In their setting, I mean, in my case, I have a gamma applied to the derivative in time. In their case, they have gamma multiplied by the derivative space. And in their case, the difficulty is coming from the fact that you have terms that do not have enough regularity, and you want to multiply. And of course, if you can do the transformation that I was mentioning, this is reducing, because from a product, you go to a single object.
Exactly.
Yes. Here, I was also thinking of that, and I went through that. Somehow my situation seems somehow different, but still is, I mean, it's clear that when you have products, it's not good. You prefer to have a single object, even information, but yeah.
No, but okay, so we thought about the same. So
this was something that came, yes, and I thought, okay, let's see there. But
you know, there are some complications. I mean, it's not solving everything because you need to set everything. You have infinite dimensional and so forth parts, which works. So it's a long story. So
yeah, it's a long story. I agree.
So it's and it is not true that it works, but if So this foundation works and might be also interesting. But
Yeah. Thank you. Yes.
you're welcome.
Okay, thank you very much, Carlo, for the question. And okay, so yeah, thank you very much. Let us thank Sandra and Nicolas for the great talk.